was alive in the presence here for 3 years, and it's still a lively presence. And has been tuning a new direction for him that he sort of started when he was here. The dynamics of black hole binding spirals and conservation effects and so on. And we're going to do the latest.
Thanks. Thanks a lot. It's great to be back. I'm actually going to be talking about two related subjects having to do with binary black hole mergers today. Please, if you have questions, ask them. If we don't have time to get to the second topic, it's not the end of the world. The first talk will be based on a paper that will be coming out shortly that I worked on with Guli Lockhart, who's one of my summer students, and Sterl Finney, who's a professor at Caltech. And the second half of the talk will be focusing on two related papers that came out in February and just a week ago today that I've worked on with Uli Spirhaki, who's a postdoc at Caltech, moving on to Barcelona, and Emanuele Berti, who used to be a postdoc at Caltech and is now faculty at University of Mississippi. So here's an outline. The overall theme of both talks is going to be binary black hole mergers, which for those of you that don't know, the idea is if you have two widely separated black holes, they orbit each other. They emit gravitational radiation that carries away energy and angular momentum from the system. It's extracted from the orbit, so the binary is in spiral. They ultimately merge to form a final black hole. And that black hole generally will be spinning. And furthermore, if the gravitational radiation is not emitted isotropically, but is preferentially emitted in one direction rather than another, by conservation of momentum, the final black hole produced will recoil with respect to the center of mass of the binary. And so generically, there'll be a recoil, and we're interested in that as well. The first half of the talk will deal with what is the biggest spin you could get from a black hole produced in a binary merger. I'm going to give a little history about theoretical limits to understand what the biggest spin might be. I'm going to describe a new calculation I did that gives you a new fundamental limit to black hole spins from binary mergers. And then I'm going to talk briefly about the implication of this calculation for looking at equal mass mergers. Finally, in the second half of the talk, we're going to look at a different case. In the first half, we're going to be focusing on black holes whose spins are aligned with the orbital angular momentum. If you're trying to make a maximally spinning black hole, you'd want to line up the spins of the black holes with each other and with the orbital angular momentum so that they add coherently. Astrophysically, there's no reason to expect the spins should have to be aligned. So in the second half of the talk, we're going to look at mergers where the spins are not aligned with the orbital angular momentum. In that cases, the black holes will tend to spin. The spins will tend to precess during the merger. And it turns out that for realistic astrophysical initial conditions, they'll precess in such a way as to line up the spins with each other, which is kind of a relativistic analog of something known as Cassini states that you see in planetary dynamics. And the fact that near merger, all these spins will be aligned with each other will have implications for the distribution of final spins and recoils you'd expect for astrophysical mergers. So, spinning black holes. In 1963, Roy Kerr discovered the unique axisymmetric stationary solution to Einstein's equation. And that is the Kerr metric that you see here. This metric is described by two parameters, m, which is the mass of the black hole, and a, which is the spin of the black hole. Relativists tend to use units where g equals g Newton's constant and c, the speed of light, equal 1, in which case the actual spin angular momentum of a black hole has dimensions mass squared. Here, this classic A parameter has dimensions of m, so that's the spin angular momentum divided by the mass. And when in terms of dimensionless limits, A star, or what I sometimes refer to chi, is the dimensionless spin. That's the spin angular momentum of the hole divided by the mass squared. And for this Kerr solution, unlike the Schwarzschild solution, the singularity is not just a point at the center of the black hole, but it's a ring. And when A star or chi gets above 1, that ring singularity, its radius increases and gets larger than the size of the horizon itself. So for spins above this maximum Kerr limit for the dimensionless spin of 1, you don't have a black hole anymore. You have a naked singularity that's not hidden behind the event horizon. So the Kerr metric itself has a limit to the kind of spin, this maximum spin a black hole can have. The question is, will astrophysical black hole mergers realize that upper limit to spins? And some people have argued that they could. James Bardeen in 1970, just a few years after the Kerr metric was first derived, showed that a non-spinning black hole could spin all the way up to this Kerr limit
after accreting a reasonable amount of mass. And so what Bardeen was, he looked at the minimum stable or innermost stable circular orbits of black holes, unlike a Kepler potential where you can have an orbit of arbitrarily small radius. For black holes, there's something known as an innermost stable circular orbit that depends on the spin of the black hole. Interior to that radius, there are no circular orbits, so the particle will just plunge into the black hole unlike an orbital time. And so what Bardeen did in 1970 was he looked at a test mass falling into a spinning black hole at the E dagger ms and L dagger ms are the energy per unit test particle mass and orbital angular momentum per unit test particle mass of a particle at the ISCO, or marginally stable orbit. So the idea was if a test particle directly falls in from this marginally stable orbit, the black hole mass will grow by this amount delta m, proportional to the mass of your test particle. Its angular momentum will grow by an amount delta j, proportional to the mass of your test particle. And from these two differential relations, you can come up with a differential equation for the growth in the dimensionless spin of the black hole as a function of its mass, given by this. And this is the angular momentum per unit mass and energy per unit mass at the ISCO, which are well known as functions of the spin, dimensionless spin. And you can show by solving this differential equation that if you have a non-spinning black hole of mass mi, by the time its mass increases by a factor of rad 6, and the black hole mass gets up to m final rad 6 mi, you've spun all the way up from 0 to a maximum spin. However, in 1974, Kip Thorne showed that, at least with a certain kind of astrophysical accretion, you couldn't really reach the spin 1 limit. So he considered geometrically thin, optically thick accretion disk, a Shikura-Sunyaev disk, in the orbital plane of your spinning black hole. And whereas Bardeen just assumed all your particles could magically get to the ISCO and then plunge inwards, in a real disk, there's viscosity. You have to lose angular momentum to get down to the ISCO and fall inwards. The way you get rid of your angular momentum is through viscosity that's transported. Angular momentum is transported outward in the disk. And at the same time you're losing angular momentum, you're also losing energy. Energy will heat up the disk. The disk will radiate photons. Some of these photons will make it out to infinity, but others will be absorbed by the black hole. And furthermore, there's something known as that even if the photons make it out to infinity, they can sometimes extract energy and angular momentum from the black hole as they make it out to infinity. So the fact is that whereas just as before, the positive torques you get from adding angular momentum as the matter falls inwards from the ISCO is balanced now by a negative torque due to the fact that this radiation can extract energy and angular momentum from the hole. And rather than getting all the way up to the maximum limit, you get to a limit where these torques balance. The positive torque from the matter balances the negative torque from the photons. Let's take a look at this more closely. These are radiatively efficient Shikura-Sunyaev disks. Here, as a function of the radius of the accretion disk, we look at the flux, which is normalized to unity at its maximum value, and the total fraction of the energy radiated as the material accretes inwards. This is for a black hole of dimensionless spin 0.9982, which is near but not at the Kerr limit. And so photons at larger radii, some of those can be absorbed by the black hole, and you'll preferentially absorb photons with negative angular momentum. And when you get into the ergosphere, which is this region, it's exterior to the ISCO, but still close to the black hole, there are no longer retrograde orbits. All the orbits there are rotating with the black hole. And radiation from the ergosphere that makes it out to infinity can carry away angular momentum from the black hole as well. So the combination of these effects, absorbing retrograde angular momentum and radiating positive angular momentum to infinity, means that radiation puts a negative torque on your black hole. Here we're looking as a function of the black hole's dimensionless spin. How is its dimensionless spin changing as you increase mass? The matter falling from the ISCO is providing a positive torque. This radiation is providing a negative torque. Where they balance determines your limiting spin, which is about 0.998, which is near but not at the Kerr limit. And this limit does depend on how your photons are being emitted. I is the case that in the co-moving reference frame, the photons are emitted isotropically. ES is electron scattering, where the photons are emitted with this distribution, where theta is the angle with respect to the perpendicular of the disk. And depending on which choice of photon emission you choose, you get different limiting spins, slightly different limiting spins. Here we see for the Bardeen case B, where we neglected this radiation. As you accrete mass, as you approach rad 6 times your initial mass, your dimensionless spin approaches unity. Now that we include the effects of this radiation, you're no longer approaching unity. You're asymptoting to this finite value. So how fundamental is this maximum limiting spin? We already saw that it depends to some extent on the intensity distribution of the photons being emitted. What if no photons are being emitted at all, as in the case of a black hole merger? Now we're considering the case that rather than viscosity through the disk is escorting your gas inwards, we're considering a test particle that's emitting gravitational radiation, and that radiation is carrying away the angular momentum, bringing your mass inwards. It's a very different calculation, because for the photons, the wavelength of the photons is much shorter than the horizon of the black hole itself. The photons are incoherently emitted, and so you can basically determine which ones escape to infinity and which ones are absorbed by the black hole by tracing null geodesics in the Kerr metric from beginning at your accretion disk in the equatorial plane and just finding how many of those null geodesics go out to infinity, how many of them are absorbed by the hole. For gravitational waves, in general, you're going to be orbiting on an orbit whose radius is larger than the radius of the horizon. And these waves are emitted coherently. So this is a wave process. It's a classical wave process. And you have to do a different calculation to determine what fraction of the energy in the gravitational radiation is absorbed by the black hole.
Just,
Yeah.
if we get into this, of course, there is a third possibility that you have radiatively inefficient.
Right, yeah, I'm not going to talk about that, but certainly the limiting spins from that, as opposed to the Shapiro-Sunyaev disk, are different, and they could be much larger in the case of a radiatively inefficient disk. I agree. Any other questions? Then we'll continue. So there's a different way to calculate what fraction of the energy and angular momentum is absorbed by the black hole, and the way to do it is black hole perturbation theory. So people have probably seen Einstein's equation. G mu nu is the Einstein tensor, which is constructed in terms of the Ricci tensor and the Ricci scalar. This represents the geometry of space-time, and it's on the left-hand side of this equation. T mu nu is the stress energy tensor from matter. It's on the right-hand side of the equation. And the two are related. That's the theory of general relativity. This is generally a nonlinear equation that is very painful to solve numerically. But you can make a lot of progress in the test particle limit where your perturbations are small. So we're looking at the case, we're considering a test particle falling into of mass little m, falling into a black hole of much larger mass big M. Q is the mass ratio of the two. You can consider the test particle to be a tiny black hole. And we're considering the case where Q is much, much less than 1. In this case, both the matter perturbation due to the test particle and the metric perturbations due to the gravitational waves are small compared to the background Kerr spacetime. These small vacuum perturbations can be fully described in terms of a complex Weil scalar, psi 4. C alpha beta gamma delta is the Weil tensor, which is the vacuum part of the Riemann tensor, for those of you that are familiar with GR. And psi 4 is a complex scalar. The real and imaginary parts essentially correspond to the plus and cross two different polarizations of gravitational waves. So for all the vacuum perturbations to the metric are fully described in terms of this scalar. And so what we're going to do is, this is a function of the geometry. We're going to linearize the nonlinear Einstein's equation in terms of the Weil scalar. And the equation governing the Weil scalar is the Teukolsky equation. We've gone from the nonlinear Einstein equation we saw before to a linear Teukolsky equation. And not only is this equation linear, but it's separable. So we can decompose psi 4 into an angular part here. This is a spin-weighted tensor spheroidal harmonic, but it's not so different from the Weil M's that you guys have, the spherical harmonics that you're aware of. And this is the radial component to psi 4. And this radial component obeys a wave equation, which is the linearized form of the Einstein equations. Here's Einstein's equation, geometry on the left, stretch energy on the right. Here we have the equation for the radial component of psi 4, geometry on the left, stress energy on the right. This is just decomposing the stress energy tensor into parts that are sourcing each component of the Weil tensor. This is a stress energy tensor sourced by our inspiraling test particle. Once we have our solutions for psi 4, we can calculate the energy and angular momentum fluxes out to infinity and the energy and angular momentum fluxes down the hole. And we do that calculation with the Gremlin code, which is general relativity and extreme mass ratio limit that was provided generously by Scott Hughes. And what we see that's kind of interesting is for the large spins that we're considering when we're trying to see what the maximum spin you can get, the gravitational radiation produced by this inspiraling test particle is superradiantly scattered from the black hole. The radiation goes downward towards the horizon with some amplitude, it scatters off the potential, and then it goes off to infinity, carrying more energy and angular momentum than it had when it was coming inwards. And here we calculate the energy and angular momentum that's been superradiantly, SR, superradiantly extracted from the black hole as a function of chi, which is the dimensionless spin of the black hole, which we said is always less than or equal to 1, and R, which is the radius that our test particle is in spiraling to. We start with the test particle out at infinity. We have it in spiral to some finite radius R due to the loss of energy and angular momentum. We calculate psi 4 and hence the energy and angular momentum fluxes. And this is the part that is being absorbed by the black hole. These are actually of negative amplitude, so we're actually, for these high spins, extracting energy from the black hole. And so as before, we had a negative torque, which was supplied by the fact that retrograde photons were preferentially absorbed by the black hole, and also inside the ergosphere, you were extracting energy and angular momentum as you went to infinity. Playing the role of the photons now is the gravitational radiation that we've calculated, which is supplying a new, different negative torque on the larger black hole. Its torque balance is the same as we saw before. This is the plot. These are both from Kip's 1974 paper. We saw matter was falling from the inwards from the ISCO, which was spinning up the hole. Radiation was extracting angular momentum from the hole. We found a limiting spin where those two balance. Now, this is the energy and its angular momentum extracted from the black hole as a function of R, as our test particle spirals inwards from large R. The four different curves on each of these plots corresponds to 4 different spins. It looks greenish here. There's a green, blue, black, and red curve. That corresponds to dimensionless spins of 0.996, 997, 998, and 999. Because a dimensionless spin chi is the orbital angular momentum divided by the mass squared, when you extract angular momentum, you're obviously spinning down the hole. When you extract energy, you're reducing the mass. Since the mass appears in the denominator, you're actually increasing the dimensionless spin. And so the actual change in the dimensionless spin per unit test particle mass is essentially the difference of the angular momentum added minus the energy extracted. We see here these curves are corresponding to the change due to the negative torque due to gravitational radiation. These horizontal straight lines are the positive change when the matter actually falls inwards from the ISCO. And these torques balance here when the black curve at the ISCO equals the black horizontal line for a spin of 0.998. So it's kind of surprising that these two very different ways of torquing your black hole lead to the same asymptotic final spin. We see here, just as in the case that Kip considered, whereas Bardeen saw everything could spin all the way up to this maximum limit, when you include a radiation torque, either for isotropic radiation or electron scattering radiation, you asymptote to this limit of 0.998. Here we see these blue curves are the same Bardeen curves. If you start at some lower spin and accrete mass, before you would have spun all the way up to 1. Now, including the fact that you're extracting angular momentum due to gravitational radiation, you're asymptoting to this value 0.998, which is quite similar to the limit that Kip found. So this is a calculation that was done using perturbation theory, which is correct in the test particle limit. But what's interesting is this tells us a lot, not just about test particle mergers, but about, you can extrapolate upwards and try to see what could it tell you about comparable mass mergers as well. So to study comparable mass mergers, the technique you use is numerical relativity, and Harold here works on numerical relativity. This is showing as a function of, again, we're looking at aligned spins. S over m squared, orbital angular momentum over, spin angular momentum over mass squared is the dimensionless spin of your black holes. This plot is for equal mass black holes. -1 is maximally spinning anti-aligned black holes, anti-aligned with respect to the orbital angular momentum. +1 is maximally spinning black holes positively aligned with respect to the orbital angular momentum. As a function of that spin, what is the spin of the final black hole produced? And we see that it's very difficult to simulate in the maximally spinning limit. People argue that it perhaps is around 0.95. This whole Franz Pretorius in 2005 was the first person to successfully merge black holes in the rim. Got a question there?
In that graph, what's the mass ratio?
This is equal mass mergers, so Q equals 1. That's what's shown in this graph. Franz was the first person to do these kinds of simulations successfully through a merger, but their simulations are restricted to spins that are not at the maximum limit, but spins of less than 0.9. So pretty much you get into trouble around here. And this is for equal mass mergers, but in terms of the published literature, they've only published simulations with mergers, mass ratios greater than 0.1. Because trying to resolve the horizon of the smaller black hole and the fact that you have more orbits per increase in frequency as you in-spiral makes it much more numerically intensive to do small mass ratio mergers. Yes, Aaron?
The spin of 0.9 is not a fundamental limit. It's just the limit of convenient, easily constructed initial data.
Right. No. I was not, yeah. When I said simulations are currently limited to, not that fundamentally they could never be done at higher spins. Yeah, I mean, people at Cornell and stuff are working on constructing better initial data, but in terms of the published literature, I think there's not a lot of reliable quasi-circular mergers at 0.9. Above spins above 0.9.
It's a head-on merger with 0.99.
Yeah,
It's only head-on.
I've actually asked people like Mark Shield and tried to get a straight answer. Is it somehow harder to do that with quasi-circular in-spirals instead of head-on in-spirals? And I think there are reasons that it is. We'll talk more about that later. Do you have a question, Chris? Okay. So here we see this is perturbation theory is valid in the test particle limit. Simulations to date, though again this is also not a truly fundamental limit, are restricted to comparable mass ratio mergers. So you'd think that they're living in different portions of parameter space and it would be hard to directly compare the two. But just because it's hard doesn't mean it's not worth trying to do so. And people have. So Hughes and Blanford, Scott Hughes and Roger Blanford in 2003, did one of the most naive things you could imagine, but it's a good starting point. They assume that the mass of the hole produced in a merger is just the sum of the two masses. M1 is the larger mass, remember, M2 is a smaller mass. And M2 is reduced by the fact that you've got some gravitational binding energy at the innermost stable circular orbit that depends on the spin of the larger hole. And the spin of the final hole, they argued, is just the spin of that large hole plus the orbital angular momentum the test particle had at the innermost stable circular orbit. And so while this will be correct in the limit that M2 is much, much smaller than M1, it's manifestly not symmetric in those two. And so if you're thinking about a comparable mass merger, it's not obvious why you'd want, you would want something that's symmetric in those two things. So Bonanno, Kidder, and later in 2008 made a revised prediction for what masses and spins could be. This one is manifestly symmetric under exchanging ratios 1 and 2. They made the obvious change of adding the spin of the smaller black hole, which had been neglected before. And they just assumed for the final mass that it would be the sum of the two initial masses. I wrote a paper shortly afterwards saying that you could also try to incorporate the fact that energy is lost during the in-spiral in a symmetric way, which reduces in the limit that M2 is much, much less than M1 to the Hughes and Blanford result. Here, M is the sum of the two masses. Mu is the reduced mass, M1, M2 over the total mass. And now we're going to try to see we did this new calculation to see how much energy and angular momentum were superradiantly extracted from the hole. How does that change our predictions for the final masses and spins? This should be exact in the test particle limit. Now we're just trying to see if we boldly extrapolate up to comparable mass mergers, how well do we do? And in fact, we do very well. Here is, this is chi I, this is the initial spin. So we're looking at two black holes with equal dimensionless spins aligned with the orbital angular momentum merging. This is in the test particle limit. What is the change in the final spin per unit test particle mass? The black curve is our new result, showing that for d chi f dq positive, greater than 0, that means you've got a positive torque and you're spinning up your hole. For d chi f dq negative, less than 0, you have a negative torque, you're spinning down your black hole. We see if you start with a, well, a still highly spinning hole and you're starting creating test particles, it's positive, you spin up to this new fundamental limit we derived at 0.998, and then you've got balance. If you had a spin even greater, you'd spin down since this is negative. Before, with the blue thing, you just had the Bardeen-Hughes-Blanford results, that you could spin up all the way to the maximum limit, but then you'd reach 0 there. These green and pink curves are derived from numerical relativity fits to the comparable mass simulations they've done. So you consider merging spinning holes at comparable masses and then just do a polynomial fit in the mass ratio and then extrapolate downward to the test particle limit. This stays positive all the way up to 1 and beyond. So this is kind of a warning as to the dangers of extrapolating to those small ratios. So it gives you, the numerical relativity can get you in danger if you naively extrapolate to the test particle limit. Even for equal mass mergers, here we see these are numerical relativity results for the final dimensionless spin of merging equal mass black holes whose spins are either 0, anti-aligned, that's negative, or extrapolating up and trying to imagine equal mass maximally spinning mergers. And you see that these are the numerical relativity determined values. Some of them have been determined very accurately with this new Caltech Cornell code. And just extrapolating using the formulas I showed them. Taking this formula and pushing it all the way up to the equal mass limit, we get a predicted spin that is incredibly close to the numerical relativity value. So it's kind of surprising. Should you really trust these at these comparable mass mergers? Perhaps not. But the fact that these are so close tells you that the ultimate way you're going to want to predict final spins throughout the whole parameter space is to take our results like ours based on perturbation theory and the test particle limit, numerical relativity calibrated results for comparable mass mergers, and extrapolate from both directions and try to find a unified predicting formula. So that's kind of the conclusion to the first half of this talk. I think we're pretty much on schedule. General relativity allows black holes to spin all the way at this Kerr limit, dimensionless Kerr limit, A star equals 1. The spin of real astrophysical black holes will depend on how they built, how they were assembled, either through black hole mergers or accretion. Kip showed in 1974 that for thin disk accretion in the equatorial plane of a spinning black hole, you can only spin up to this finite value, 0.998, less than the Kerr limit. We showed that if you build a black hole through test particle mergers based on gravitational wave inspirals, you get this same limit essentially coincidentally. And ultimately, the final few graphs showed that the way to predict throughout the entire parameter space of mass ratios and spins what you should get, perturbation theory extrapolating from small mass ratios is a valuable tool, and complements extrapolating downward to low mass ratios using numerical relativity. Yeah, Andrew?
Yeah. So with this superradiant energy, like,
Yeah.
how much mass do you sort of wind up losing at the end? Is it a couple tenths of a percent? Like,
How much is so for a black hole there's a gravitational binding energy at the ISCO, and that binding energy can be very large. It can be like 40% of the rest mass for a maximum spinning black hole. The amount of energy that's energy that you lose to gravitational radiation from your test particle as you move inwards. In addition, you're extracting energy from the hole itself, and that also depends on the spin of the black hole. It can be, I think in terms of the rest mass, it depends on the spin. It can be, I think, as much as 1% or so. I think that's what we showed. That's what we showed back here. So this is the energy per unit test particle mass as a function of black hole spin. So this is 0.999. So it's about a little between 1.75 and 2%. So a few percent of the rest mass of the particle is not only just radiated to infinity, but is extracted from the hole itself.
and then for the equal mass case, how much less?
For the equal mass case, for non-spinning, so so you're saying you can say at wide separations, I know what the sum of my two black hole masses. When I breaking down what fraction of the energy came from what, the perturbation theory approach doesn't make sense there, but you can say, if you think of the final mass of the black hole, what is that compared to the sum of the initial masses?
For equal mass non-spinning holes, it's about 95% of the sum of the initial masses. For maximally spinning holes, it's about 93%, so about 7% of the mass is radiated away in equal mass mercury. The second half of this talk deals with spin precession, which is, so in the first half of the talk, we were looking almost exclusively at cases where the spins were aligned with the orbital angular momentum, which made sense because we were trying to see what is the biggest spin we can get. You want to line everything up so they add coherently. But generally, astrophysically, there's no law saying that the spins have to be pointing in the direction of the orbital angular momentum. People have argued that gravitational radiation gets very weak as a steep power in R when the black holes are widely separated. So you need something other than gravitational radiation to get you to a small enough separation that you can merge within the lifetime of the universe. And that something else is a torque between the binary black holes and a gaseous circumbinary disk. And people have argued that the same torque that is extracting angular momentum from the binary, allowing them to get close, is also aligning the spins of the two black holes with the orbital angular momentum of the disk. So that case has been made, but the effectiveness of how good a process this can be for aligning the spins with the orbital angular momentum depends on the nature of the accretion flow, and this accretion flow can be very uncertain. There have been some simulations that are saying there will be a residual misalignment between the spins and the orbital angular momentum of 10 or 30 degrees, depending on whether you're thinking about cold or hot disks. But this is still a very kind of preliminary process. This residual misalignment is still uncertain. It depends on the amount of gas and the kind of accretion flow. If the spins are misaligned with the orbital angular momentum, then they will precess many times between the separation of 1000 m, where gravitational radiation takes over the in-spiral, and separation 10 m, which is just a few orbits before merger, where we can start to think about studying these with numerical relativity. Let's consider in more detail this process of how the black holes in-spiral from separation of about 1000 m to a separation of 10 m. It turns out during this part of the in-spiral that can be described by post-Newtonian mechanics, there are 3 distinct timescales of the problem. One timescale is just the orbital time for the two black holes to orbit each other. This goes as r to the 3/2. This is just Kepler's law. Then there's the precession time. That's the time it takes for the black hole spins to precess. That scales as r to the 5/2. And finally, there's the in-spiral time. That's the time it takes for gravitational radiation to remove energy and angular momentum for the binary and for the binary separation to decrease. That scales as r to the 4th. So at large separations like r to the 1000 m, r to the 4th is much bigger than r to the 5/2, is much bigger than r to the 3/2. So there's a hierarchy of timescales. Orbital timescale is the shortest, precession time is scale is intermediate, in-spiral timescale is the longest. So this hierarchy of timescales allows us to simplify our study of the post-Newtonian in-spiral. The fact that the orbital time is short compared to the precession time allows us to average the precession frequencies over a single orbit. And that's what these are. S1 is the spin of black hole 1, the more massive hole. S2 is the spin of black hole 2, the smaller black hole. And they're precessing about each other with the frequencies given by omega 1 and omega 2. These are orbit average frequencies. Q here is the mass ratio of the two holes. It's defined to be less than 1. And the precession frequency depends both in magnitude and direction on both the orbital angular momentum of the system and the spins of both holes. These formulae are clearly manifestly symmetric under exchanging 1 and 2 and inverted Q. This is how the spins precess. Now the orbital angular momentum will precess as well generally. And the fact that the precession time is short compared to the gravitational wave time, the in-spiral time, allows us to calculate that as well. In the limit that on timescales that are short compared to the in-spiral time, radiation is not being carried away. So J, which is the total angular momentum, it's the sum of the orbital angular momentum and the two spin angular momenta, both in magnitude and direction is conserved. And furthermore, the magnitude of the orbital angular momentum is conserved on the precession time. And so the fact that these two quantities are conserved tells us how the direction of the orbital angular momentum should precess. This equation here is basically just saying dj dt equals 0. And therefore, dl dt is minus ds dt. So we use the spin precession that we saw on the previous slide to determine how the spin direction precesses. And finally, on the long time scale, the in-spiral time scale, the frequency, this is omega, is the frequency, your orbital frequency, omega dot, is increasing. And don't worry in detail about precisely where these numbers come from. But the point is that omega, the orbital frequency, is increasing as you in-spiral. And hence, since omega is in the denominator here, the orbital angular momentum is decreasing in magnitude. And so we see, based on the descriptions I just provided for the precession of the spins and how the orbital angular momentum precesses as well, we can see what happens to various spin distributions as we start at 1000 m and allow them to in-spiral down to 10 m. That is what was done here by Bogdanovich et al. in 2007. They took there's 1,000 points on this plane. Here we see this is cos theta 1, cos theta 2. Theta 1 is just the angle between spin 1 and the orbital angular momentum. Theta 2 is the angle between spin 2 and the orbital angular momentum. Bogdanovich looked at 1,000 randomly oriented binaries separated by 1000 m. The spins are pointing in random directions. In-spiraled those 1,000 binaries down to 10 m. Plotted on this plot what is theta 1 and theta 2 at this final separation. Said these points seem to be pretty much randomly scattered about this box. You would expect cosine theta to be flat. For a random distribution, you'd expect cosine theta to be flat between -1 and 1. And argue that isotropic distributions remain isotropic, and therefore we need to start thinking about gaseous torques to understand, to try to align spins with the orbital angular momentum. We considered not just isotropic distributions, but non-isotropic distributions as well. And in fact, even though 1000 m seems like a large separation from the perspective of general relativity, from the perspective of astrophysics, 1000 m is a very small separation. And therefore, as we see in these gaseous torques, they are the ones that are setting the initial conditions at 1000 m. So here we see this is the same plot we saw before. Cos theta 1 is on the x-axis, cos theta 2 is on the y-axis. We've now color-coded the points based on the initial values of theta 1. There's, in fact, this is a 10 by 10 if you count. This is a 10 by 10 grid. There's also, each of these is 10 different binaries. We took different values of theta 1, different values of theta 2, flat distributions, and we also did a flat distribution in delta phi, which is phi 1 minus phi 2, where phi is just the traditional, azimuthal coordinate. And we took them at a separation slightly larger than 1000 m, and then just evolved the binaries inward to 1000 m, 100 m, and 10 m. And what you see is, if you neglect the colors, we basically reproduce the Bogdanovich results. That here they're in a grid, and here they're more spread out. But essentially there's a flat distribution in points entirely filling this box. But if you consider not just an isotropic distribution, but imagine just looking at the blue points. So imagine that the spin of the larger hole is partly aligned with the orbital angular momentum. Then these blue points, they don't ergodically fill the entire box by the time you get down to 10 m. But they don't stay segregated in their little part of the phase space either. They spread out. These blue points are spreading out, and I hope you can see, they're spreading up. They're spreading out along these lines to fill a portion of the phase space. And the way they're spreading out, as Racine showed in 2008, is to conserve the dot product with the orbital angular momentum of this weighted combination of the two spins. So the individual values of theta 1 and theta 2 are not conserved. But you are evolving along these lines. So you get somewhat of a change in the distribution of values of theta 1 and theta 2 between 1000 m and 10 m. And you get an even bigger change in the angle between the two spins. Here we're looking at delta phi, which is, it's phi 2 minus phi 1. It's just the projection onto the orbital plane of the two spins. Just in spherical coordinates, it's phi 2 minus phi 1. And theta 1, 2 is the angle between black hole spin 1 and spin 2. We see here the colors are corresponding to the initial values of theta 1. Blue means that theta 1 is aligned with orbital angular momentum, so cosine theta 1 is close to 1. Green is the intermediate value. Red is the anti-aligned case. That will hold true for the rest of this talk. We see here that even though the color determines the direction of spin 1, since spin 2 is still random, the angle between the two things is still flat. Cosine of that angle is still flat between -1 and 1. And we see as you in-spiral from a little bit larger than 1,000 m, 1,000 m, 100 m, and 10 m, we see in this plot, the red and the blue points, which have the same distribution up here, do not have the same distribution over here. The blue points are clustered near delta phi equals 0, cos theta 1, 2 equals 1. So they're the two, for the blue points, spin 1 and spin 2 have become aligned with each other, whereas for the red points, they become anti-aligned with each other. They're clustered down near plus or minus 180 degrees. Cosine theta 1, 2 equals -1. Schmidt, when was in a paper in 2004, was the first person to take into account this change in the spin distributions. If you look at a histogram, black is our full 1,000 binaries. Blue is the same blue points we saw before that are initially aligned. The spin 1 is initially aligned with the orbital angular momentum. Red is the points where the spin of the more massive hole is initially anti-aligned with the orbital angular momentum. At 1,000 m, you've got this distribution given by these dotted curves. It's flat in cos theta 1, 2, flat in delta phi. By the time you in-spiral to 10 m, the black distributions are still flat modulo shot noise, Poisson noise, but the red and blue distributions are no longer flat. The ones where S1 was aligned with Ln now are peaked towards cos theta 1, 2 equals 1.
What's the difference between the 4 panels?
Well, these are the top panels. We're looking at cos theta 1, 2. The bottom panels we're looking at delta phi. This is for a mass ratio of 9/11, which was the value that was studied by Schnittman and then studied by Bogdanovich as well. We wanted to compare with their results. This is for a mass ratio of 1/3, so a smaller mass ratio. The effect is much more prominent for near equal mass mergers. It's still here, and this is not the best plot. It's still here for this mass ratio, but it's less significant statistically. The main point is that if the spin of the more massive hole is partly aligned with the orbital angular momentum at a separation of 1,000 m, the two spins will be aligned with each other when they finally reach 10 m. And that has implications for the spins of the black hole that will be produced and the gravitational recoils. Here we see, again, black, red, and blue are showing us the same things we saw before. The dotted curves are, if you imagine the spin distributions at 1,000 m stayed constant all the way down to 10 m, what would be your distribution of final spin magnitudes? Whereas the solid curves are saying if we take into account the spin precession that we're looking at, how does that change the expected distributions? And whereas the black, solid, and dotted curves are basically the same, if you look at the blue curves, you compare this blue dotted curve here to this solid blue curve, it's peaked towards higher values. By aligning the spins with each other, they're adding coherently so that when you merge, you produce a black hole with a larger spin. And this effect can even be even bigger if the spin of the more massive hole is initially more closely aligned with the orbital angular momentum. Here we see there's solid and dotted curves on this plot, which again are the dotted curves. Imagine what would be the final spins we get from a distribution at 1,000 m. The solid curves are saying what is the spin distribution we'd expect if we allow precession to occur down from 1,000 m to 10 m. The different colors, this purple, blue, and green, correspond to misalignments of 10, 20, and 30 degrees. The yellow, orange, and red correspond to misalignments of 150, 160, and 170 degrees. These are nearly anti-aligned. These are nearly aligned. And we see there's a big difference between the dash and solid distributions, tilting you to much larger, shifting you to much larger spin values. This is just the manifestation of what we saw before. If you align the spins with each other, you're going to get larger final spins.
Well, the upper envelope doesn't change. The upper envelope doesn't change much.
The upper envelope has not changed much. These are maximally spinning mergers. But the mean of this distribution has shifted significantly to the right. Here you get, there's a big peak of very large spin values, whereas this is much broader all the way down to 0.7. And it changes the directions as well. The colors are the same as in the previous plot. Theta final now is the angle between the orbital angular momentum right before merger and the spin of the final hole. And it's actually strange, you get a complete shift. In this case, if you compare the nearly aligned to the nearly anti-aligned case, whereas before it makes sense that if the holes are nearly aligned with the orbital angular momentum, you'd expect that if the spins are nearly aligned with the orbital angular momentum before merger, it makes sense that the spin of your final black hole would also be nearly aligned with the orbital angular momentum. Whereas before, when the things were misaligned, you could have much larger disagreements. Now, the fact that you're aligning the spins with each other means that the final spin magnitude is bigger, and therefore the misalignment with the orbital angular momentum can be even greater, because the sum of the spins is contributing more to the final spin than the orbital angular momentum was. I guess I'll explain that more slowly for people that are interested near the end of the talk. Finally, we want to look at what are the effect on gravitational recoils. I've stared at these formulas for a very long time, but for those of you that haven't seen these, as we said before, gravitational radiation is emitted during the in-spiral. That radiation does not have to be isotropic, but can instead be preferentially in one direction, in which case, by conservation of momentum, the black hole will recoil in the opposite direction. And these recoils can be as large as 4,000 kilometers per second, which, in terms of relativity, compared to the speed of light, 4,000 kilometers per second is not a very large number. This is about 1% the speed of light. In terms of astrophysics, in terms of the escape velocities from galaxies, this is a big number, kind of a worrisome number. These kicks have multiple contributions. There's one contribution that has nothing to do with spins, just due to the asymmetry of the masses of the two holes. Then there's two spin-dependent contributions. And as Latham and I showed in a paper while I was a postdoc here at CITA, this spin-dependent contribution to the kick, that depends on a weighted difference of the spins. So the basic idea is if precession from 1000m to 10m aligns the spins with each other, then the difference of the two spins will be smaller, the kicks will be smaller. We look here, these are the same colored plots we've shown before. The dashed curves are the distributions you get if you just assume the distributions at 1000m merge with those same spin distributions. The solid curves account for spin precession from 1000m to 10m. Because the spins align with each other, the spin contribution to the recoil is less. Here, this is just a histogram of recoils as a function of velocity. Once you include precession for the partly aligned cases, you're peaked at much smaller values. We see here, this is using the formula I showed previously from the Rochester Institute of Technology group. For different mass ratios, what is the median recoil you get from the merger, and what is the, if you think of the cumulative distribution, 90% of them will be less than this value V90. If you just took the distributions you had at 1000m, you could get large, worrisomely large kicks. If you allow the spin precession that we've been studying to occur from 1000m to 10m, you get these much reduced recoils, which is reducing most of the recoils below the escape velocity of galaxies, which means galaxies can keep their black holes after mergers.
So what's theta 1 again?
Sorry, excuse me?
What's theta 1 again?
Theta 1 is the angle between the spin of the more massive black hole and the orbital angular momentum at 1000m. The dash distributions are if they merged with that distribution they had at 1000m. The solid curves are if they merge with the proper distribution if you spiral down to 10m. And so it's for the partly aligned case, you reduce the spins, reduce the recoils. For the anti-aligned case, you actually boost the recoils. But the anti-aligned case is somewhat less physical. You wouldn't expect black holes to anti-align with their accretion disks.
So this is because you actually, if you start with the anti-aligned case,
If you actually,
it's trying to go towards smaller numbers, towards the orbital plane where you have the big kicks.
exactly. If you, so what, yeah, why, so you're saying why is this boosted?
Yeah.
I didn't actually talk about this because I'm already running out of time, but there's a second effect. Not only do you align the spins with each other, remember we said this S naught is conserved, which is this weighted sum of spins? So S naught is conserved, remember you saw all those in the theta, cos theta 1 versus cos theta 2 plots, things were moving along those lines. Those lines were not lines of constant projection of spin in the orbital plane, but constant S naught in the orbital plane. And so the effect of that will be to boost the spins by bringing S naught into the orbital plane. That's why you get this boost. But I am at the end of my talk, and it's a good thing because I'm totally out of time. The point of the second half of the talk was that misaligned spins, which is what you generically expect, will precess many times as the black holes in spiral from 1000 to 10n. Although we confirmed the Bogdanovich result that completely random isotropic distributions stay isotropic, those are not the correct astrophysical conditions to use at 1000m. You need something to bring your black holes close enough to merge within a Hubble time. That something will probably partially align the spins with the orbital angular momentum. Once they are partially aligned, gravitational radiation takes over the in-spiral. You in-spiral to 1000m, and depending on the spin and mass ratio of the holes, you can greatly align the spins with each other. And when you greatly align the spins with each other, the final spins will be bigger because they act coherently when you merge. And the recoil velocities will be less because the spin contribution to the kick is sourced by differences in the recoil. So that's the end of the talk. Thank you very much.
So this isotropic distributions remain isotropic. Seems like something that might be able to attack analytical techniques, kind of Liouville phase-space density.
You would, yeah. I mean, I've thought about that. I haven't made much progress. You wouldn't. Yeah, it seems if you look at these separate distributions and you see they're aligning and anti-aligning with each other, it seems remarkable that that the whole thing would cancel out to leave an isotropic distribution isotropic. There have been a bunch of other papers by the Rochester group. Herman and collaborators had a paper where, I'm not sure what the Herman collision was. The Rochester group claimed that they did see a small but statistically significant change in the distribution, even for an initially isotropic one. They have more computers than we do, and they started their mergers at 50m instead of 1000m because they weren't aware of this spin alignment effect. So it would certainly, I don't know, within certainly the 1000 binaries that we ran, isotropic distributions stayed isotropic. Whether that's true to if you have an arbitrarily large number of things would be interesting to see. They argue it's not, but I'm going to go there at the end of the script, so I'll talk a little further about it. Any other questions?
So what's the reason for the big spread? I mean, for these different angles, you can get a whole bunch of different recoil velocities.
So we consider these are just the black is a fully isotropic distribution that I showed before. Red and blue are the 30% ones that are aligned or anti-aligned. Here we fix the angle theta 1 at 1000m between the spin of the more massive hole and Ln, but the spin of the second hole is still completely random. So the biggest thing resulting in this big spread is that the spin of the second black hole can be completely random. And this is a mass ratio of 9/11, so it's a nearly equal mass ratio. So that's giving you a big spread in spins or recoils.
Are you going to comment on how well you expect the test particle fluctuation to hold for Q or 1, for large spins?
So it's. Oh, we can go back to that slide. I'm talking about that a little bit more. It's kind of amazing that it works at all. It's a test particle calculation that you're extrapolating all the way up to Q equals 1. KLP is Kesden, Lockhart, Finney. This is the predictions, including the Superradiant extraction in this paper. K is my earlier thing, which included the radiation during the in-spiral, but not this Superradiant extraction. BKL is the earlier Buonanno-Gator linear prediction, which neglected the energy radiated during the in-spiral.
So the neglected the binding energy.
Yeah, they neglected the binding energy.
Much bigger effect in the superradiant scatter.
Right, which is not the binding energy for a highly spinning case, like Andrew asked, could be 40% of the rest mass, whereas the actual superradiant.
But even for the case of.
Even for these guys, it's not 40%, but it's still more than the 1 or 2%. And also the superradiant thing very much falls off tremendously in the spin. Because the ISCO, you can think about it geometrically. We know that the innermost stable circular orbit radius depends on the spin. It's at 6m for non-spinning holes. It goes all the way down to m for maximum spinning holes. And so you imagine just the size, subtended by the horizon at the ISCO, which is some, crude kind of way to think about, what fraction of the energy is absorbed by the black hole, will very much, changes as a function of spin. So I agree with you, that the superradiant thing is a smaller effect. And these are a variety of different AEI, FAU, and Boyle Kesden. These are a variety of different predictions from numerical relativity. These are numerical relativity calibrated predictions trying to match numerical relativity simulations. So the fact that these things agree with this is not a great surprise. But that this agrees well, suspiciously well. We wanted to try to break that agreement. And so we first I added the energy radiated during the in-spiral, but instead of breaking the agreement, it made it even better. Now we include the superradiant scattering, makes it even better still. It's very suspicious. To be devil's advocate, this KLP prime is another guess, another different extrapolation of the equal masses. That we wanted to have the right symmetry properties. We wanted the test particle limit to reduce to the right thing. But that doesn't fully describe how you would extrapolate up to maximum limit. And to be devil's advocate, I chose this different extrapolation, which you see, it's still surprisingly good, but not quite as freakishly good as this is.
So what about the anti-aligned spin?
The anti-aligned spin, these are non-maximal spins. We get further away. We get further away. It doesn't bring you in the right direction. Including the energy radiated does, but including the energy extracted does not. The real problem is that in the test particle limit, there's people think of a merger. There's an in-spiral stage, a merger stage, and a ring down stage. During the in-spiral, the stuff radiated scales linearly in the small ratio. And this extracted stuff, even though it's smaller, still scales linearly in the small ratio. Whereas the ring down contribution scales quadratically in the small ratio. So it makes sense to neglect it in the test particle limit. But for equal mass mergers, the energy radiated after the formation of a common horizon is still a significant fraction of the total energy radiated. So what you want to do is look at the ring down and then extrapolate that upward as well. That's a future project. And also looking at the transition to plunge, which is going to be the subject of a paper that's in the works, scales as some intermediate mass power and mass ratio between 1 and 2. So you think that would be, at least in the test particle limit, more significant than the ring down, and logically should be the next effect to consider. But I keep expecting to break this, and it keeps behaving better and better. It's kind of suspicious.
Well, I'm sure Mike will be happy to.
Yeah, I'm going to be around the rest this afternoon, and I'm going to be around all day Wednesday, so please stop by, tell me what you're working on, and I'll be happy to tell you more. What?
You're here today or Wednesday?
I'm going to Perimeter on Tuesday, so I'll be, at Perimeter all day Tuesday.
Okay, thanks.
Yeah, thanks.